Hello. Good morning, everyone.
Good morning, sir.
Good morning. I think the last day of the sessions, people are tired, it seems. Okay, so let's start. Not many people have joined, but let me start anyway. Yeah. Yes. So can you see my window, please?
Yes, sir.
Thank you. So today, the last day of the workshop, the last day and first session, and then after this, we'll have another session that will be taken by Professor Partha, and then we'll have the test. Okay. So far we have looked at a number of predictive modeling techniques. We looked at pre-processing, started with pre-processing, then we looked at regression, then time series, then neural networks. So today we'll look at some case studies. We'll look at some case studies, how we can apply these models in our research domain. So I'll be using predicting flows in software-defined networks. So any of you who have heard this name, software-defined networks? Have you heard this software-defined networking? Anyone? No one. You have not heard software-defined networking?
No, sir.
Okay, fine, no issues. Okay, software-defined networking, this is the new, so my research area is networks. Okay, I don't work in predictive modeling, but I use them as tools. So this is my research domain, networks, network and security, computer networks, network security. So I'll be talking about a little about software-defined networking because I need to define my problem. So what is the objective of this talk? The objective of this talk is how to define the problem from our research domain and use the tools, predictive tools. So I'll talk a little about software-defined networking and then how it differs from our traditional network. And then we'll look at the problem formulation, how the problem has been formulated. Then I will look at the architecture, the proposed work architecture and dataset. Then the prediction model. So I'll be using two prediction model, ARIMA and SVR. So ARIMA we have already seen in detail, so I'll not talk about ARIMA much. I'll talk a little in detail about ARIMA, SVR, support vector regression, same as support vector machine, you can think of. And then the implementation and results. So this will be the first part of my talk, and if I have time, then in the second part of my talk, I'll be looking at data sources, means from where we can collect our data. So this is the outline of the talk. So let me start with software-defined networking. What is software-defined networking? So software-defined networking is the new network paradigm. Okay. And if you look at most of the corporates, so if you talk about Amazon, Microsoft, Cisco, the pioneer in computer networks, so they have all started using software-defined networking. They have all started using software-defined networking. Some people call it software-defined networks. It's all the same, and in short, we call it as SDN. And what is its main function? How does it differ from our traditional network? Okay, it differs from traditional network in the sense that it decouples the control and the control layer and the data layer. or the control plane and the data plane. So what is this control plane and data plane? So control plane, you can think of control plane as the brain of the network. You can think of control plane as the brain of the network. It decides how to route the packet and how to provision the resources and all those stuff. And data plane is task is it says where to forward the packet. It says, so you tell him that a packet which has come from port 1, you forward it to port 3. So data plane can do it, and it can do it very efficiently. So its main task is switching, okay, moving the packets from the input port to the output port. So that's all you need to know about it. So control plane is the brain of the network. It decides which route the packet will flow. Okay, and data plane, it just switches the packet from the input port to the output port, and it does it very efficiently. So now in SDN, what we do, we have divided this into two separate entities, and this one we have made it centralized, the brain. So, and how do we achieve this? We achieve this using the SDN controller. So all the control plane comes and gets located out here in the controller. So if we have multiple controllers, then we'll have issues of scalability and availability. Okay, so multiple SDN controllers are deployed for scalability and availability, and there's a dynamic switch to control assignment. So these two statements will become more clear if I go to in the next few slides. This will become more clear. Okay, so this is what I said about traditional network and SDN. So if you look at traditional network, you see there are two planes. One is the data plane, which is for switching, and at the top is the control plane. So then what are these? These are all network elements. This is a network element. This is a network element. What is a network element? It can be a switch, the one which you use in your lab, the switch. It can be a switch. It can be a router. Okay, these are network elements. And each network element, there is a control plane and a data plane. So what happens here means, so when it receives a packet, so now this particular switch will decide where to route the packet. Okay, because it has got a brain of its own. It has got a control plane of its own. Now, if you come to software-defined network, you see I've moved all the control plane and placed it in one machine, which I call it as the controller. Okay. So now, so if you look at the network elements now, they only have the data plane. So when a packet comes in from here, it goes out here. So there will be several output ports, several input ports. So it just needs to move a packet from the input port to the output port very fast. Okay. And then the control plane, yeah, anyone? Any questions? So and then all the control plane are located here in the controller. Okay, so this is this is the basic idea behind software-defined networking. Means the controller is centralized. So what is the advantage of centralizing the controller? Now the controller has the map of the entire network. It has the map of the entire network. Okay. So it can efficiently decide where to route the packets. It can efficiently decide to provision the resources. So you see it's sitting at the top. So if you go to the next slide, you can see the control plane is sitting at the top. The control plane is sitting at the top. So I've just blown up that figure, the last slide. Now here in this case, they just have in traditional scheme, they are just having the packet forwarding hardware here, and then an OS for the control plane. Here they have minimal operating system, and the control plane is located here. So now it has a map of the entire network, the control layer. So it can efficiently decide which route will be best. Okay. Here locally, it has to decide in this distributed manner. So let's see how it works. Okay. So I need to know how it works to define my problem. So let's say I've got a sender. Let me call this as S. I've got a receiver. Let me call it as R. Okay. And I've got several switch S1, S2, S3, S4, and so on. So and this is a SDN network. Okay. So each of these switch, what will do? It will just forward the packet. And how it will forward the packet? It has a table known as a flow table. It is a table which is known as a flow table. When a packet comes, it looks up the flow table and checks whether that particular destination address is present here or not. And so initially the flow table, let's say initially there's no packet in the network. So initially all the flow tables are empty. Now this source sender, it sends a packet. Okay, it sends a packet and the destination is R. It sends a packet to R, let's say. It sends a packet to R. Now this switch S1, it looks up, it says, looks up for this destination R. It looks up for the destination R is empty now, right now. Empty right now, the flow table is empty. So it doesn't know what to do. So it contacts the controller. It contacts the controller. So this is, it sends a packet saying, I've got a packet for receiver R, but I don't know how to route the packet. Please tell me. Okay. Fine. Then when the controller receives this, so since the controller has the map of the entire network, okay, then the controller can now run its own algorithm and decide how to route the packet. So the controller decides and says that the best way to route the packet is through S1, S2, and S3. So the controller, what will do? It will send the information. So the packet has to flow through S1, S2, and S3. So it sends out this message, flow mode message. So basically what we'll do is this will populate this table. So it says that for switch R1, it will say if the receiver is R, then it says send it to S2. Okay. And then for S2, it says if the receiver is R, then send it to S3. And then when it comes here, then it says when the receiver is R, then it is in the same port, so it's output into that port. So maybe some Ethernet port, ETA0 something. So this is what it does. And then the controller also tells switch one that, okay, now I have populated all the table, I've set up the route, now you can send the message, now you can forward the packet. This is the packet out. Now the sender now this switch S1 looks up, okay, looks up the packet. It says, okay, the destination is R. It sends it to S2, so the packet goes here. Then it looks up the packet. So here the destination is R. Then output port is S3, so it goes here, and then R, the output port is ETA0, and then finally the packet lands up here at the receiver. So this is how SDN works. So means where now the next time when the sender sends a packet to R, it doesn't, then the switch S1 need not look up, need not contact the controller, because it's already there in the flow table. So the packets which the switch sends to the controller for new flows, these are known as flows. Okay. So this is how SDN works. Fine. So now, if I have a single physical controller, then what is the problem? What are the issues? What are the issues of a centralized system? Yes? Anyone?
Yes, sir. I have a question.
Yeah, please.
Sir, once this route is mapped, now switch 1 knows that it has to pass to switch 2 and switch 2 knows it has to pass to switch 3. So will this
Yes.
route be followed every time, or does the controller decide every time the packet comes in which routes should be followed?
No, so when you for each of these, there's something called as the TTL, time to live. Okay. So this route will be active for TTL time period.
Okay, okay, sir. Okay, got it.
Okay. So the thing to understand here is, so when now if sender S was up, so if there's some now new receiver R1 out here, which is connected out here. Okay. Now, if the sender sends to R1, then you'll check up the R1 is not here. So it again has to connect to the controller. So the sender doesn't connect to the controller every time. It means the switch doesn't connect to the controller every time. Only when a new flow comes, it contacts the controller. So I was asking, so this is a centralized system. Advantage, it can see the entire network, okay, and decide which route to follow. But what are the disadvantages of a centralized system? What are the disadvantages of a centralized system? What do you think will be the disadvantage?
Sir, every time the controller has to decide and the switches they have to wait for the instruction from the controller. Is it? So the time gap that is involved in packet in and packet out.
Yeah, so that is one thing that we'll try to minimize. Okay. There's one thing that we'll try to minimize. So there are ways in which means we can have dedicated this one wires between the controller and the switch. But in general, for a centralized system, what are the disadvantages of a centralized system? So one is like, so there's a single controller. Okay, there's a single controller. So if this single controller fails, then the entire network fails. So there's a question of single point of failure, right? There's a question of single point of failure. And then if there are, as you said, if there are a number of flows, then it will not be scalable. Then it will take more time. Okay, so it's not scalable. Not scalable. So these are the two main issues of the centralized system. There can be a single point of failure and it's not scalable. So these are advantage. You can do centralized network provisioning. You can decide who will get what, how much, and all those holistic management, granular security, and all those stuff. But there's a problem of scalability and high availability. Means if one of the controller fails, then the entire network will fail. So what the designers thought, that they thought that we'll have a distributed kind of a network, means distributed controller plane. So this is a logically centralized, okay, logically centralized, but physically distributed. Logically centralized means all this. So now you can see here, there are, instead of putting one controller, we have put 4 controllers out here in the control plane, and they are all synchronized among themselves. So each one can see the entire network. So that's why we call it as logically centralized. So it is like a centralized controller, each one. Okay, but there are multiple controllers, and if one of them fails, then the other one can take up the task. And to make it scalable, as you said, the flow time will increase. Okay, so what I'll do is, to each of the controller, I will map some switches. So for example, to controller C1, switch S1 is mapped. Okay, to controller C3, switches S2, S3, S4, S5 will be mapped, and so on. So this is how they are mapped. So it means this controller takes care of S1, this controller C3 takes care of S2, S3, S4, S5. So how do I decide which controller will take care of which switch? Depending on the traffic, right? Depending on the traffic. If this switch is generating a lot of traffic, then this switch S2, S3, S4, S5 combined, it is S1 is generating more traffic than combined of all this. Then I'll put them all in a different network and this one in a different controller. All of S2, S3, S4, S5 in a different controller, and S1 in a different controller. But network, okay, the network traffic is highly dynamic. Highly dynamic. Okay. So after some time, what will happen is this S1 will not be, or we also call it as, if you have heard the word, bursty traffic. Means you are watching a video, right? You're watching, so at a time, a lot of traffic will be coming. So there's now meeting going on, so a lot of traffic is going on. But after some time, the meeting will end, okay, and then there's no traffic. So this traffic will be highly dynamic. So at some point of time, S1 will be generating a lot of traffic, but after some time, S1 doesn't generate, and S2, S3, S4, they started generating a lot of traffic. Then what will happen? I'll delete this mapping and I'll start map. I'll map S1, S2 with C1. So is this clear? So this is my problem. This is my. So I need to understand this to define my problem. Okay. So my idea is that how can I decide this mapping beforehand? Okay. So what will happen is what happens is S1 starts generating a lot of traffic. So there's congestion in the network. So we do the remapping. So that is like the problem has set in, and then you are looking at the cure. So our objective is how to make it proactive. Means the mapping. So what I do is I divide the time into time steps. Say T1, T2. So I at this epoch I decide what is the traffic, and looking at the previous traffic, I decide whether the traffic will remain the same or it will increase. Okay, and depending on that, I do the remapping so that when I go to this epoch, then there's no congestion. Similarly, I do it here, do the remapping so that whenever I switch from one epoch to another epoch, then there is no congestion in the network. Otherwise, in the traditional way, what happens is, so in this time period, so there is congestion, then you start moving the switches here and there, okay, remapping, then you go again, so every time there's a problem, then only you do. So it's a reactive kind of thing, but we want to make it proactive. So this is my problem statement. Okay, so the first thing is you need to find a problem statement. So people say, well, if you've done your PhD, you know how much of time you need to spend to find a problem definition. So predict the network traffic to map the switches with the controller. Predict the network traffic to map switches with controller. So this is my problem definition. Now, so prediction has come. So I can use prediction model, and then this is a time series. So I'll use time series modeling techniques. Okay. The problem definition is clear?
Yes, sir.
Okay. So fine. So so this is how this is my architecture. I take the raw data. Okay. I take the raw data, and then I do some transformation, wrangling, okay, to convert it to a time series. And then after that, I do the pre-processing, and then I look for outliers, missing values, and also all those stuff. Then I look at I use two prediction models. One is ARIMA and the other one is support vector regression. So for ARIMA, I need some parameters, PDQ. So ARIMA you have already done in detail. So I'll not be looking into ARIMA, but I'll look a little more in detail in support vector regression, since we have not covered this in the workshop. Okay, so let me first come to data. So data is very important. So the first thing is you need a problem definition. So once you have the problem definition, then you start looking for data. From where do I get the data? So to get the data, so I'll talk about a little about data at the end of the talk. So means when you're looking at data, then you should look for those data sets which are universally acceptable. So you should get the data from some standard repository, so that people can verify your work. You give the source of the data set, and then you give the parameters of your experiment, so the people can independently verify, and then the acceptability of the work becomes much more instead of generating your own data. So the data set is very important. So here we use two data sets. One is from the Center for Applied Internet Data Analysis, and we call it as SCIDA. The other one is from a data center, which is the University of Wisconsin. Okay, we collect data from these two sources. So SCIDA, if you look at SCIDA, this is a organization which is purely involved in data collection, monitoring and data collection. So it has built large infrastructure to support data collection. And these data sets are used by network people all around the world. So we use this data set, and this data set is for an internet backbone. So it is a very large scale network at the backbone of the network, internet. So there will be very high data flow out here. And then the other data set we look at is for a data center. So here the volume of data is less. The volume of data is less, and the data here is from 3 data centers, and this is provided by the University of Wisconsin Medicine. And the URLs for the data sources are also given. So if you look at the data, then the data will have, so this first part is the source address. This is the source address. This is the destination address. This is the number of packets and bytes, and so from A to B, B to A. So this is how the raw data looks like. IP address, the port number. Okay. Then this is the source IP address, source port number, destination IP address, destination port number, the number of packets, the number of bytes, then the time, the relative start time, the duration of the session, and all those stuff. The raw data. So what I do is I sample this data set because there are a lot of there's millions and millions of such lines. Okay. So what I do is I sample them. Okay, I sample them means I take a window period, say some 5 seconds, okay, and all the flows in that 5 seconds, I collect and put them together. So just the raw data, I sample them. Okay. So this is how I change the form from one data set to one form to another form. Sampling. I do a sampling, simple sampling. I take a time period, a window period, and then in each window period, the number of flows, I just add them up. Okay. So this is my initial data, and then after sampling, I get this samples, sample S1, S2, S3 for a fixed window size, fixed window period, data duration period. And then after I get this, what I do is I now divide them. So I decide how many lakh values I will look into. So this becomes my feature generation. Okay. So I had the initial raw data, I sampled it. Then I decide how many features I will look, how many past values I will look at. And here I've got a time series now. So I've transferred the time series for a supervised learning dataset into a supervised learning dataset. Then I do my pre-processing part. I look for outliers. Then I normalize the values within a range. I use the min-max normalization technique. I look for missing values. All those pre-processing tasks I do out here. And then finally, I'm ready for my prediction model. So I use the prediction model ARIMA. Okay, prediction model ARIMA. So has already looked into detail in ARIMA. So I will not go into detail. So here, basically, you need 3 parameters, right? P, Q, and D. So these are the 3 parameters that I get. So how do I get this? So I first check for stationary using the augmented Dickey-Fuller test to check stationary. Then I identify P and Q using the Box-Jenkins method. which you already done in your ARIMA, this one workshop, right? So this is, so I use ARIMA as a baseline approach. Okay, then I try to compare it with SVR. So I need at least 2 approaches. So the next one, the prediction model that I look at is support vector regression, and this is same as SVM. It's same as SVM. Okay, so basically here in SVM we need 2 parameters. One is the penalty parameter C, and other one is your sigma square. Right. So SVM, I think some of you are aware of it. Okay. So up to this point, any questions? Then I can take some questions. Otherwise, I'll proceed with the support vector machine. Any doubts out here? No doubts. So for me, see, I work in this, so you see that my problem domain is software-defined networks, or I work in networks in general. So for me, all these prediction model tools are like, I don't go into depth of all these tools, right? So I just need to know what these parameters mean. What does this C parameter mean for me? Because I need to tune this. So it's like you bought a washing machine, then you need to wash clothes. So I need to know which knob I should tune. Okay, whether how much of water I must require, what is the temperature, how to set the temperature. So I need to know this parameter C, and I need to know this parameter sigma square for Gaussian kernel. So to know these parameters, I need to dive in a little. I read. So for example, if you bring your washing machine, then you need to read the manual to find out what these parameters are. Okay. So that's what I'll do out here. So I'll not go into detail, but I will just try to see what these parameters mean. So let's go back to our linear regression method that we have looked at. So if you remember linear regression, the hypothesis or your decision model is, so here what I've done is just we have parameterized there the hypothesis with theta. So I'm here parameterized with W, so that this nomenclature is standard with what is available in the literature. So A is theta x equal to theta transpose x plus B. So this is what we have seen, right? And this is my decision boundary or hyperplane. So here what we do is, so the regression model, we can also use it as a binary classifier. We can use it as a binary classifier. So I use a sine function or a signum function, and then so all the points which is above this line, I take it as positive examples. These are my positive samples. Okay, positive samples or positive examples, and all those points which are below this line, I take it as my negative samples. I take it as my negative samples. So what is signum function, sine function returns? So if this is greater than 0, then it will return 1. If it is equal to 0, it will return 0. If it is less than 0, it will return minus 1. It should return minus 1. No? It will return minus 1. So this is minus 1, and if it is 0 or 1, then I say it's a positive sample. It's a positive sample, and it is 0 or 1, 0 or greater than 0, and if it is less than 0, then I say it's a negative sample. And this is my hyperplane or decision bound. This is my decision bound. Okay. This is my regression model. So you see the regression model, it's the basic model and then the foundation of all models. Like you can start neural networks also from regression. You see how it has got different layers. So neural network has got 3 or more layers with a hidden layer, and regression has got 2 layers. So here again, when we come to SVR, so we can start with the regression model, linear regression model. So now what we say is, let's, I'm not happy with just a single line. Okay, so some points may be just out here, some points may be just be out here. So I don't know whether it's a positive sample or a negative sample. Maybe some error within that in the measurement. So I want this margin of classification to be as large as possible. So both from intuition point of view. So with more confidence, I can say that, yeah, this is a positive sample, this is a negative sample, right? And then both from intuition as well as from your probably approximately correct the theory. So I can say that I want to maximize this margin as large as possible. So larger the margin, better for me. With more confidence, I can say that these are positive samples and these are negative samples. Okay. So, so the definition, so for y equal to 1, we just change the definition. So instead of saying that W transpose X plus B, this product term plus the intercept, it is just not be equal to greater than 0, but some term epsilon. So some term epsilon, then I say it's a positive sample. And if this is less than some, again on the negative side epsilon, then it is a negative sample. And from each point, from each xi, I can measure the distance to the hyperplane using this formula. And then, so what's my objective? My objective is to maximize this classification, to maximize the margin. Okay. So I want to find W and B. So that the margin is maximized. And those data points which are exactly at this margin, these are called as support vectors. So if I know my support vectors, then I can find a positive plane and the positive samples and the negative samples. So determining the support vectors are important. In SVM. So the problem now turns out that I want to find W and B such that the margin is maximized. So now the same problem I can reformulate like this. So the norm I can formulate in this form. Okay, it's a convex optimization problem. I want to maximize the norm, minimize. So it was 1 by omega, now omega. So from maximization, I'm converted to a minimization problem. And then subject to these conditions. Okay. So now it may so happen that there are some, the training set is not linearly separable. So for example, there's a training sample which is negative, okay, but is on this line, the hyperplane, and there's a training sample which is positive but is on the negative side of the hyperplane. So what to do now? So one way I can do is so in this decision plane, instead of doing going straight, I can make it like this. And so on. Means it'll go on. Okay. So how can I do this? I can do this by introducing higher level polynomials, higher order polynomials. But if I do like this, what is the problem? What problem will I fall into? Yes.
Sir, the classification becomes difficult, right? Positive and the negative every time. I'm not sure.
Classification becomes difficult. Yes, classification becomes difficult. Yeah, that's true. So what I'm doing is I'm paying a lot of attention to the training samples. I'm paying a lot of attention to the training samples. So then this will become a problem of overfitting, right? If you introduce a lot of higher level polynomials, then it will become problem of overfitting. So what I do is instead of so I say some error is acceptable to me, some misclassification is acceptable. So we introduce some variables which are known as slack variables. In fact, there's one slack variable for each data point. So for each data point, I introduce a slack variable. So if the data point is positively classified, means the slack variable value is 0. Otherwise, there will be some misclassification value. So for this particular two data points, the slack variable values will not be 0. Right. So this type of function is known as the epsilon intensive loss function. Okay. So now my problem definition changes slightly. So now it says I want to maximize the margin. Okay. I want to maximize the margin, and then I want to minimize the classification. So margin was 1 by omega. So omega means I want to minimize this, means I want to maximize the margin. Okay, and these are the slack variables, and these are the slack variables. And so this parameter C, this is very important. So the parameter C has come now. Okay, the penalty parameter, or is also called as the, so if you are using high level higher order polynomials, so then this will become the regularization term, right? So this is also known as the regularization parameter, or the penalty parameter. And so this is how much of weight you give to the misclassification, how much of weight you give to the misclassification. So I need to understand, so to understand this C parameter, I need to know all this. So I will not go into how the problem definition, how the problem has been formulated, but I want to know what is C. Right. So if C, I set C to 0, then it becomes my previous problem. Right. Means I want, so if C is 0, then all that I want to do is I want to maximize the classification margin. And C can vary from 0 to infinity. So if C is very large, then what does it mean?
Too much acceptance of errors.
Too much acceptance of error.
Sir, C
is very large. See, you just note this, okay? So
the misclassification will be more.
Sorry?
Misclassification will be more if C is very large.
Okay, you just try to understand this problem formulation. Okay, so this value will become very large. Okay, this value will become very large, and I am trying to minimize it. This value will become very large, and I am trying to minimize it. So what does it mean?
Model is more precise.
Model is more precise, exactly. So model is more precise means I am not accepting misclassification.
Misclassification.
Right. I'm putting a lot of weight to misclassification, and I'm trying to minimize it. Minimize the misclassifications. And when I'm putting C equal to 0 means I don't care about misclassification. Misclassification, I don't care. Okay. I'm just trying to maximize the margin. Okay. So what is C? C is a trade-off between the misclassification and the width of the margin. So if you put a lot of weightage on the misclassification, then your model will become more complex. So it's like saying the trade-off between how much of error you'll accept and what will be the model complexity. So the larger the value of C, the more the model will become complex, and less error prone, but more complex. So when I say C is infinite means I am not accepting any misclassification. So it's an optimal hyperplane. It's an optimal hyperplane. Okay. So that's why this value of C is very important. I need to know how to set this. I cannot set it very high. I cannot set it very low. So if I set it very high, what will happen is if C is very large. So if C is very large, then misclassification will become 0. Okay, it will be minimized. Okay, but the classification margin will reduce, and the classification margin will also be reduced. But my aim was to reduce increase the margin. Okay, so whereas if C is very small, or C is small, then my misclassification will increase, but my margin will also increase. So that's it. Now, to solve this problem, what we do is we convert into a dual problem using the Lagrange's theorem. But I don't need to know. But what happens is with each variable there is an alpha I associated. Okay, and alpha I will not be 0 for all those values which are support vectors. And I just need to know the support vectors. And all of these depends on this product term. The solution depends on this product. So this is a dot product if these are just numbers, or you can say this we call it the inner product for vector space. So the solution to the linear classification problem reduces to finding this inner product. That's what we need to know. So that's the thing that we need to know from here. So just to summarize linear SVM, what is linear SVM? These support vectors, the support vectors determine the hyperplane. So hyperplane, what is a hyperplane? This is a decision boundary, and its dimension will be 1 less than the dimension of the data points. Its dimension will be 1 less than the dimension of the data points. And the support vectors determine the hyperplane, and the optimization algorithm is the quadratic optimization algorithms can identify which training points are the support vectors. And for that, we don't need to compute the weights explicitly. The solution depends on the inner product. Or we also like another way of writing this is this. So this is the key point out here. That the solution depends on the inner product. So when in SVM, this is the key point. You'll see why this is the key point when you go to kernels. Okay. Okay. So now let's say linear versus non-linear SVM. What is linear SVM? Linear SVM says the data sets are linearly separable with some misclassification. We'll tolerate some misclassification, but more or less the data is linearly separable. Okay. And what's our aim? Our aim is to maximize the margin. So, but what if the data set is not linearly separable? We can introduce a lot of higher order polynomials. If you introduce a lot of higher order polynomials, the system will become more complex, compute intensive, and there will be problems of overfitting. So what SVM does is it tries to map the data to some higher dimensional plane where it is linearly separable, where it is separable linearly. So that's the basic idea of SVM. Instead of using higher order polynomials, it tries to map the data to some higher dimensional plane where it is linearly separable. So let's take some example here. So if you look at this, so it's a one dimension. We can think it as a number line. And there's no way I can separate this data set, the positive examples and negative examples. But if I map this to a two-dimensional plane, x1, x2, now it becomes linearly separable. Now it becomes linearly separable. And how do I map this? I map this using some mapping function, psi. Okay, so so let me give an example. So what will be this mapping function out here? For this example, so let's say these are my data points. Let me say this is -1, -2, -3, -4. Okay, 1, 2, 3, 4, 5. So what I do is I square this term. I square this term, then it becomes, so this will become, this point will become, this point will become -525, right? This will become -416. This will become 416, 525. No, right? -39, 39, and so on. This is okay. So what is this mapping function? Psi of x. Or x1 is equal to, I'm mapping this to x1 and x1 square. Right? Hello?
Yes, sir.
Okay. Yeah.
Yes, sir.
Keep on responding, otherwise it becomes.
Yes, sir. This is very interesting. We are enjoying. Go ahead.
Okay. No, you keep on responding, otherwise I don't know. Means whether you are getting it or not. So what I'm doing is I'm mapping it to a higher plane. Okay. So from 1D, when I map it to 2D, then it becomes linearly separable. Then it becomes linearly separable, right? So now, another example you can take here. So here this is a 2D, and when I map it to 3D, so then it becomes linearly separable. So what will be the mapping function here? The mapping function here will be like, say, is x1, x2. Then the mapping function here will be x1 square root 2 x1 x2 then x2 square. So if you map it, so this psi function, if you take this psi function, then you'll get this hyperplane. Then you'll get this hyperplane. And you see if you look at this one, the coordinates of the hyperplane is 1 less than that of, so these are all 3D points. These are all 3D points. And this is, the hyperplane is 2D. So this particular hyperplane is able to separate the data set linearly, which was not possible when it was at a lower dimension. But now when I map it to a higher dimension, then I can separate it linearly. So that's the basic working principle of SVM, or you can say SVR also. Okay, so what are the steps involved? The steps involved are, I need to find a function. I need to find a function psi of x. I need to function psi of x. Then I need to map the data from n dimension to m dimension, where m is larger than n, using this psi function, the mapping function. Then to get a decent boundary, what I do is I need to compute the inner product. if you remember, I said the main point is to find the inner product to compute the support vectors, right? So so now the problem has become, when I map it to a higher dimensional plane, it's become a problem of linear SVM. Okay, and for linear SVM, all I need is the inner product. So you see, when I do this for millions and millions of points, and when I map it from 2 dimension to very high dimension, then this becomes very, very, very compute intensive. A lot of parameters are involved. So is there a better way of doing it? So the better way of doing it is this kernel function. The kernel function will solve this issue. So that's now, so I got my first parameter C. Okay, now I need to know my second parameter, that is sigma square. And I'm doing all this just to know my sigma square parameter. So let's take an example here. So I have 2 data points, 1, 2, and 3, 4. I've just taken randomly. So you can think of this as x1 and this thing as x2. Okay. And then this is the mapping function. Okay. So this, what it does is it maps x1, x2 to this vector, x1, x1 square, and so on. So what I've done is I've computed it. So I've done it the hard way. So I compute it for each of the mapping function, for each of the points. Okay. I compute. So when I map it to the higher dimension plane, this 1, so it becomes like this 1, then x1 square, x1, x2, root 2, x2 square, and so on. Similarly for y, I do it y1, y2, I do it like this. And when I compute the inner product, then I get 144. And what I said is, this is all I need. For the linear SVM, the inner product is all I need to compute the support vector. So if you see, so what you see here is, I've done all this mapping and all the stuff, but finally what I do is I get a scalar product. After doing all of this hard work, what I do is I get the final output is what? It's a scalar product, scalar quantity. Sorry, not a scalar product. Product is scalar, means it's a scalar quantity. So the question now is, can I get this value directly without doing all these steps? And the answer is yes, you can do it using the kernel function. So if I have a kernel function, and just to remind you, not all functions are kernel functions. There are some theorems, Mercer theorem, and all those. You need to know that. So those people who work in machine learning, they need to know this. But for me, what I all need to know is there is a kernel function which can directly compute this, the inner product. So the kernel function here is 1 plus xi transpose xj. So if I this, yeah, this for x and this is for y. So if I do this, okay, then I compute, then I see I directly get 144. Okay, is this clear? The example?
Yes, sir.
Okay. So that is what you see everywhere. What is written as the kernel trick. So what is the kernel trick? The kernel trick, it says the linear classifier relies only on the inner product between the vectors to find the support vectors. Now, when we map every data point to a high dimensional space, then the inner product can be computed using a kernel function. So basically means you don't need to do all this hard work of mapping the data into higher dimensional plane, because all I need to find is the inner product. And a kernel function is a function that accepts inputs in a lower dimensional and it turns the inner product of the transform vectors in a higher dimensional space.
Sir, I have a question if I may ask.
Yes, sure, sure.
Sir, the question is, if the dimensions are 4 or higher, will the kernel still work or will have to use something else?
No, the
4,
kernel
5
will work.
dimensions.
The kernel will work. So means basically what I do, I'm not computing. So I'm not at all computing this. I'm not at all computing this.
Okay.
All I'm doing is without computing this mapping, I'm just computing the inner product.
Okay.
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 And then if I have the inner product, then it becomes linearly separable. So if it is linearly separable, then I can find the support vectors. I can find the support vectors.
So do you mean it will go on xi, xj, xk, xl, xm?
Yeah. It can go to any.
Okay,
Then,
but it will be more compute intensive, right?
yeah, it becomes very compute intensive. So that's what I've tried to show in this example. It becomes very compute intensive. Just
Got
for
it.
when you are mapping from 2 dimension to how many this is 6 dimension, right? When you're mapping it to very high dimension, it will become more compute intensive.
So for example, sir, if we take 4 dimensions, k, xi, xj, xk, xl, what will be this transformation? What will this transformation look like? 1 plus?
This one. So this for every x, I have to do this.
Okay, so you will do xk transform
Yeah,
into
yeah.
xl. Okay.
Yes. That's what I've done here.
Thank you, sir. Thank you.
So that's all I need to do. So that's why they call this as a kernel trick. So if you look at SVM, everywhere you'll find this term kernel trick. Well, so what is this kernel trick? The kernel trick is that you don't need to map the data into a high dimensional plane to get the hyperplane. So a kernel is a function that accepts input in a lower dimensional and it returns the inner product of the transformed vector in a higher dimensional space without having to compute the mapping of each data point. If you have to compute for millions and millions of points, then it will become very compute intensive and this method will not be used. So these kernel functions are the core out here. These are the core things out here. Okay. And defining these kernel functions is not simple. So this is where people are investing a lot of their research effort in defining these kernel functions. And so our job is to, since I'm not a machine learning expert and I'm not going to try to find a new kernel function. So there are a lot of kernel functions, but the most common among them is the Gaussian kernel function. So everywhere you'll find that people use this. But there are also some other kernel functions. So I've given here, tried to give a flavor of some of the kernel functions which are available. One is your linear kernel function. So when I say linear kernel function, it means no kernel. You're not using any kernel. So psi x is x itself. Your regression. So when I use this, I can use this when I have a large number of features, but the training sample size is very small. So you have to understand when you use this. Okay. So if you have large number of features, but a small training sample, then you use this linear kernel. And then the example that we saw just right now. So that's an example of a polynomial kernel. So here P is the degree. So in the example we use quadratic. But the most common and the powerful and popular kernel is the Gaussian kernel. And this we use when we have relatively smaller number of features and a very large training sample. And you will see that this is the case for most of our day-to-day problems that we face. Okay. We have small number of features. We don't have large number of features. Means, so if my training sample size is millions, 10 million, then my number of features will not be 10 million. It will be maximum how much? 10, 20, 30. Okay. So if you look at the number of features will be when the features is small. Okay, when the number of features is small, but the training sample size is very large, then you use the Gaussian kernel. And for Gaussian kernel, the main parameter, so the main variable here is what? By sigma square. my sigma square, right? So now I need to find out. So now I know the two parameters. What are two parameters? One is C. I know there's the penalty parameter. Okay. There's a trade-off between the margin and the error of classification, and sigma square. So what is sigma square? Sigma square, if you take a large value of sigma square, then you will have high variance and low bias. High variance and low bias. So what does it mean? In simpler terms, high variance means it problem of overfitting. So it means you're putting a lot of emphasis on the training samples. You're putting a lot of emphasis on the training samples. A lot of emphasis on the training samples. And if you have low variance and high bias, means you're trying to maximize the model. Okay. So now the question is, now how do I set these parameters, C and sigma? So if you are working with any SVM problem, so these are the two questions that will come to mind. That you need to face. Okay, and if you have gone through all this workshop in all the last 4 days, you've seen that all of this depends on the data. Every model depends on the parameter depends on the data. So how do I set this? So the best way to set this is using cross validation. Using cross validation, right? And then you have already seen what is cross validation. What is cross validation? I think in ERIMA also we looked at cross validation. What is cross validation? Yes.
Sir, we are checking the accuracy.
Yeah, we are checking the accuracy, but what do you mean by cross validation?
Whether the same will fit outside the sample or not.
No, so question, it's question of fault. Okay, means, so I have my training sample, right? So I have my training sample. One is, I have got my training sample. I've got my training sample. And then how do I use my training sample? So what I can do is I use the training sample to train my model, and then I use some other to test it. Okay, but now then I'm not testing the model. It means I don't know how well the model has been trained. Okay. So other way is I divide it into one random this one. So this is my training sample and this is my testing sample. But so you can have here multiple faults here. So if I say I use, say, let me how many, say 4 fault. So what I do, I train with this 3, okay, and then I test with this one. So I divide my data into 4 chunks. So 4 fault, 5 fault, 3 fault, whatever. Okay. So I train with this 3 and then test with this. So next what I'll do, I'll train with this, I'll train with this, I'll train my model with this, and then I'll test my model with this. And then next I'll do with the same for you. I'll train with this, I'll train with this, I'll train with this, I'll test with this, and I'll train with this. Okay. So that's how I find my value for, and then for every time I keep on tuning it. So I don't make it very large because then the model will become very complex. So here also I don't make it very large. Okay, it'll have a high variance. And then, so I try to tune this parameter and then tune this parameter depending on my data set. Okay, so that's all about SVM. That's all about SVM or SVR when we use it for regression. Then, so when you were, so just to remind, so we have spent a lot of time in SVM. So just to remind, so what I had my data set. Then I did some wrangling and changed the form. Then I did pre-processing. Okay. I did pre-processing. Then after pre-processing, I used two models. One is my ERIMA. One is my ERIMA, and the other one is SVM. Now, so now then after this, I need to check. So I now have got the results. Now I need to check the performance. So I use this performance metrics. One is the normalized root mean square. Why I use, so this is your root mean square. This is your root mean square, which you have already seen. Okay. This is my root mean square, the square of the errors, and take root. But I use normalized root mean square since I'm using multiple data sets. So I use the mean, normalized root mean square. And the other one I use is the mean absolute percentage error. This is the error. So how much error is there and what is the root mean square. So these two are the performance metrics that I use. And these are the results that I got. So I use two data sets for KIDA 1 and KIDA 2. These are my data sets. And this is the university data set that I was talking about. So here you see this data set is smaller, so and it's more linear. So here if you see ERIMA performs, the comparisons are almost, the performance is comparable with ERIMA and SVR. But for large data set with high non-linearity, okay, yes, very high non-linearity, then for such cases, what you see is SVR is outperforming ERIMA. And then I do this for different sample size. And these are my mean absolute percentage errors. So this is one of the papers that we have published in a conference, and then we are working on it to publish on we have submitted to a journal. We're using some more reinforcement learning kind of model. We have it for journal. So that's all I have for this SVM part, the first part. Then these are my prediction results. So let me not go into this. Let me talk a little bit about data since I've got some time, 10 to 15 minutes. So if you have any questions, then I can take some questions from the first part. Any questions? No questions. Okay, fine. So, so now the question is, how do I get my data? So from where do I get my data? So that's the question that I'm trying to answer in this next few slides. So there are two ways in which you can collect data. One is your primary data. Primary data, if you look at primary data, they are authentic. They're from authentic source, highly reliable, and unaltered by human beings. So it has all the qualities that we want. Whereas secondary data, where do we get it? So just like what I got it from KIDA. So there is secondary data from some secondary sources. I get it. So Kaggle is one place where you can go and search for data. A lot of data is there in Kaggle, and there are also a lot of other sources. So depending on your domain, you have to find out where your data is. So, but what I'll talk about here is how you can collect data. So that's one thing that I'll talk about here. How do we collect our data when we are doing it for experiments? So one is you can collect data from an experimental setup. So I work in the area of network security, so I need data, right? For introducing detection systems, IDS, and all those stuff, you need to get data. And nowadays, all of the IDS, they work on machine learning. So what I do is I set up an experiment. So I set up an experiment. So here in this example, suppose I've got a server here, and I've got a client, and I attack the server using the client. So I install some denial of service tool out here, and then I send the attack packets to the server, and then here I use some program to collect the packets. Okay, so these are designed for a specific research goal. So basically I want to, when I'm looking for DDoS attacks, denial of service attacks, or distributed denial of service attacks, then maybe I can use this. Okay, it's for a specific research goal. Then you tune the, then you tune the parameter, you can tune the parameters, you can tune the objective, but what that it's on a small scale. But the disadvantage is here everything you have decided beforehand. Means you're thinking that the attacker is going to use this tool, particular tool, but attacker may use some other tool. You don't know. Or attacker may not use this method at all. It may use some other method. Reflector attacks, a lot of attacks possible. But I have not taken care of that. I'm just taking care of one way of how the attacker will attack my machine. So you are not capturing the unforeseen data. So it is not practical. That's why most of this synthetic data, when you do this synthetic data, then you see that the papers are not acceptable. If you send it to very reputed journals, they'll say your model is not tuned to the real world data. So this is you don't have real world. Your model is not tuned to the real world data. So the second way that you can generate data is using your survey or interview data. So you must be frequently getting emails. You must be frequently getting emails that I'm doing a research on this particular. So kindly fill up this survey and all. But most of the time people are lazy to do this. So here, let me give a specific example. So in the last semester, one of my BTech students, two of my BTech students, they were designing a chatbot. They were designing a chatbot for academic queries. Chatbot for academic. So you know what is a chatbot, right? So chatbot means it's a robot kind of thing. It's a software where you ask questions and the robot will answer the question on behalf of the organization. So during registration, during when new students come, or even when they are all students, so we find that there are a lot of queries from the student side. So they'll ask, which courses do I need to register in this particular semester? Where is the registration going on? What are the prerequisites for this particular course? And so on. So what we did is we tried to design a chatbot which will answer all of these queries. So in the chatbot, when you are designing chatbot, the main engine of the chatbot is something called as the dialog flow. The main engine of a chatbot, you can use different models, but in the model that we use, this dialog flow, and this is one of the common way of doing things. Okay, dialog flow. So what this does is it tries to capture the intent of the query. It tries to capture the intent of the query. So for example, I'm asking, what are the courses that I need to register? So the same question I can ask in different ways. Which courses do I need to register? How many courses do I need to register? So all of these, so this is an NLP model. So this particular platform, it needs to be trained to capture that all of these three questions have the same intent. It is asking basically the same question, means how many courses do I need to register? So how do I get this data? So for this, what I do is I design a survey. And I say, so what are the questions that you need to ask? And then I send it to the students. So this is how I can collect data using the survey mode. And then there are data which you can collect from systems. So for example, this CCTV camera, when you collect data from such systems, they have all the characteristics of big data. So they have volume. It means you will get lots of data, velocity, and then it can be structured, unstructured, multiple forms. And then there will be veracity, means uncertainty due to data inconsistency, latency, and so on. So these are some examples of found. So this kind of data are called found data. So you can collect it from traffic loops, smart meters, social media mining, and social media and crowdsourcing platforms. And one way of collecting this data from social media or other platforms is web scraping. Web scraping, so web scraping, you can use two tools. One is your APIs. APIs are basically nothing but a function call. A function call is a communication protocol between a client and server. And other ways you can use, you can automate the process. So basically, I want to spend some time here. So APIs, if you want to scrape data from Facebook, so you want to find out how to get data from Facebook, then you can contact Facebook. They'll give you an API along with a token. And then using this token, you can get data from the Facebook. And this API is based on your REST API. And this is a standard way of defining the APIs. And then you can query data using for the nodes, for the posts, for upload pictures and all those stuff. But using this API, you cannot collect much of data. So it means there's some restrictions in this data. We are working on a project and we found a lot of restrictions. So this is how the API of Facebook looks like. So what I want to spend some time out here is how to automate my data collection process. So suppose I want to go to some e-portal, and then I want to say I'm looking for how to predict the laptop price. Okay, so the laptop price this semester, and then what will be the in this quarter, and what will be the laptop price next quarter. Okay. So then I need to go to some e-portal site and get the configuration of the laptop, the price. So that I can do manually, but I cannot get much of data. So maybe 100 or 1,000 at most. Okay, so then I can automate the process. So to automate the process, I need these three things. I need a web driver, I need a parser, and I need a general purpose programming language. So let me show you a demo of how we automate things. Can you see you can see my window, right?
Yes, sir.
Okay. So let me see how we can collect data. So let me run a notebook, Jupyter notebook. So this is for running Python program. Yeah, so it has started running. Yeah. So I've got this Python code. So let me see if it runs. So this is the Python code. So basically, when you are scraping, so scraping means you're automating the data collection process. So there are three things that you need. One is your Selenium. Selenium is nothing but this particular software. This is used to control your browser. It's Selenium. So here you need to give the driver of the browser. So here in this, I'm using the Chrome. I'll be using this Chrome as my browser. So I need to give the driver of Chrome driver. And then once I get control of the Chrome, then I need to scrape the data. So for that, I'll be using Beautiful Soup, and then that is used for. So this the next code is for from Beautiful Soup. So I'm trying to go into some portal, and then I'm putting my username, password, and then I'll automate the process. So let me run this. Let me run this and show you. Some error. It's not a code route. Yeah, you see, it has opened the Chrome window, no? Can you see?
Yes, sir.
Yeah, then you push the username. It waits for some time, puts the password, it will automate the process, login, logs in, and goes to the, it searches for laptop. And then it will scrape. So it's, yeah, so you see at the search, this one is put the laptop and then it scrolls. And then we put this in a file. So this is how we can scrape data using, so that's what I wanted to show you here. So this is one way which you can collect data, but for this you need to do some amount of programming. Yeah, so for these you need this web driver, and then for parsing you need Beautiful Soup, and then some programming things, and then these are some text on how to use Selenium, the web driver. So you need to define the part of the driver. You're using Chrome, the ePortal website, the username, the password, and then scroll. So these are some commands on how to do this. Okay, so let me stop out here. Let me not go into a lot because there are a lot of programming details out here. So let me not bore you. So if you have any questions, then I can take some questions now. Yes, any questions?
In web scraping, you said that there are restrictions, right? Suppose you want to download a very large data set. Is there a way so that you can download, let's say, millions of rows of data and some thousands of columns? Or there will be restrictions everywhere? Sites themselves put some restrictions, right?
Yes, sites. So, like for example, you cannot scrape Facebook. It's not legal.
Correct. So we need to be careful about that.
Yeah, you need to be careful about that. Okay, and then even if you are scraping some site, you if you try to scrape very fast, then they will object. Okay, then they
Correct.
block you.
Per
So
day there are some limits, per hour there are some
yeah,
limits,
so
right?
what you can do is like, so you try to mimic that like you're doing it for a human being. Okay, so what is it? I think it's here. Okay. So what we do is, so if you look here, is we give some sleep time here. Okay.
Right, sir.
So you
So
let
this
let it sleep
5 is 5 minutes, right?
5
Or
seconds.
5 seconds, okay.
Yeah, if you sleep for 5 minutes, then it will become too long. So we make them sleep. So just because it's a small program, so you can go directly also. But just to show you, I put here 5 seconds.
Because I think, sir, corporates are not using web scraping to that extent anymore. What is your opinion? Is that correct?
Corporates depends on what kind
For
of.
research, for example, suppose they want to do some market analysis, right? For that, they have to go through some 100 websites and want to collect some data which is in a tabular format. So 3-4 years ago, they used to do that, but I have seen companies closing down their web scraping teams and doing I mean, manually or maybe using some other process?
Yeah, nowadays a lot of tools are available. For example, for Twitter, if you want to scrape Twitter and all, then you don't need, you can use TweetPy, those tools are there, right? So you can use those.
Correct. Right,
But
sir.
but the main issue is with some of the sites, they are very, their privacy rules are very
So
strict.
there are a lot of ethical issues as well, right, sir?
Yes, there are a lot of ethical issues. So you cannot scrape everywhere.
Thank you, sir. Thank you.
So you have to be careful when while scraping. Yeah, you are right. You have to be very careful. Yes. So any more questions? Okay. So if there are no more questions, then I'll stop out here. Then the next speaker will be Partha. He'll be again, he works in data distributed computing. So he'll give some idea of how to use distributed computing for how to use predictive modeling in distributed environment. And then from 2 onwards, we'll have the quiz. So it'll be for 45 minutes, 45 questions. That's what I planned. Okay.
Right, sir. Thank you. It was a great session, sir. Thank you very much.
Thanks a lot.